Hi, Assalamualaikum. My name is Raja Aizat Azim bin Raja Karul Azli. My number metric is S73034. And today I would like to present question 1. So basically question 1 required to generate a discrete time signal graph. And next, the length of the signal xn is 61 since n ranges from 0 to 60 comprehensively. It is then required to compare the first graph x1n and second graph x2n. X1n is periodic because it has a fundamental period, while x2n is not periodic because 4.545 is not an integer, so it is not a fundamental period. Lastly, it is required to compare the frequency and shape between x1n and x2n.
The linear phase low pass filter with frequency response h omega equal to 4 times exponent of negative j3 omega for omega is less than 2 was explored. The impulse response Hd in component A was estimated using the inverse Fourier transform, resulting in a thin shaped curve centered at t equal to 3, indicating a time delay caused by the linear phase. The filter's band limiting effect was demonstrated in part B, when the input signal xt equal to sinc 4t was convolved with ht to produce an output yt that attenuated higher frequencies while retaining low frequency component. Both xt and yt were displayed using MATLAB subplots in section C to illustrate the smoothing and delay caused by the filter, confirming the theoretical impact of ideal low-pass filtering on timing and signal shape.
My name is Khalija S73071. This is the answer for question number 3, which is for A, B, and C. In part B and C, the intermediate signal Vn differs because the input signal Xn is convolved with two different impulse response, H1n in part B and H2n in part C. Convolution with different systems produce different results, so the resulting Vn signal are not the same. However, the final output Yn in both parts is the same. This is due to the associative property of convolution, which state that the order of subsequent convolution has no effect on the final result. As a result, whether Xn is convolved first with H1n and then H2n, the vice versa, the final output Yn is the same. For question number 4, this is the code and the graph that we got in this question. This is for the integration solution that we did. For question 4c, this problem involves finding the convolution of two signals. The triangular pulse is non-zero between t0.5 and t3.5, while the sinusoid starts at t0. Analytically, convolution is done by integration, the product of one signal and a time reverse shifted version of the other. However, due to the sign function and the triangle piecewise shape, the integral cannot be solved easily, and by hand is the best evaluation.
So here is the equation ht where we have to find it so that we can put it in the coding. ht equal to 1 over 2 pi integrate from negative infinity to infinity h omega times exponent of j omega t d omega. The linear phase low-pass filter with frequency response h omega equal to 4 times exponent of negative j3 omega for omega is less than 2 was explored. The impulse response Hd in component A was estimated using the inverse Fourier transform, resulting in a thin shaped curve centered at t equal to 3, indicating a time delay caused by the linear phase. The filter's band limiting effect was demonstrated in part B, when the input signal xt equal to sinc 4t was convolved with ht to produce an output yt that attenuated higher frequencies while retaining low frequency component. Both xt and yt were displayed using MATLAB subplots in section C to illustrate the smoothing and delay caused by the filter, confirming the theoretical impact of ideal low-pass filtering on timing and signal shape.
Assalamualaikum, my name is Hanan. I will discussion about question 6. The transfer function was decomposed using partial fraction expression. Taking the inverse Laplace transform result in the impulse response. Although the response includes a growing potential term, the system remains stable because the region of convergence ROC is RE S over 2, which excludes all pool. MATLAB function can be used to verify and visualize this stability behavior effectively.